So what we'll be covering today, I believe, is sequences, arithmetic, geometric, and the so-called hidden arithmetic sequences. I tried to dig out some old word problems from Art of Problem Solving that I did 10 years ago. We'll look at set notation, set operations, when you're given a set or you're just given Venn diagrams. We're going to also count with Venn diagrams and tables. And I believe you started propositional logic like P and Q, P or Q, those kind of things at the very end. I'm not sure how far your professor went. Okay. Check one, two. Okay, good. All right. So I guess we can get started now. So let's start reviewing sequences. So when we say that we have an arithmetic sequence, what's the rule that generates a arithmetic sequence? And you can use your microphones. It's a small group. It's fine if you'd like. If not, that's fine too. Or you can use chat. Um, so okay. I mean, an arithmetic sequence is simply one where one term is the previous one plus some constant or difference, if you will. So this is constant. Um, so if you're just even given two terms and you're told that it's arithmetic sequence, uh, obviously you can just find the difference, right? If you know that n2, for example, is n1 plus some constant, then that's easy enough, to compute. The difference is simply the difference between any two consecutive terms. Okay, so this is 3. So then we know that the next term, the n3, this is the first term of the sequence, second term, and the third term. N3 will simply be the previous term plus that constant difference that we just found. Okay. So that should be simple enough. I don't think there's anything too mysterious about this. Um, Maybe the only difficult thing would be to find a general formula, n sub, or find something like n sub 100 or something like that. And just to emphasize the point, our second sequence here, as soon as you have two consecutive terms, here we are given n7 and n8. So the constant, you're told it's an arithmetic sequence, so you know how it's generated. You take you take a term, subtract the previous term to get the difference. So this is 5 minus 7. So here the constant they're adding from one term to the other is -2. So then we can, of course, work backwards, right? So if we know that n7 is if we know that n7 is 7 and we know the difference is -2, then we'd simply subtract the -2 to get the preceding term. So that would be is 9. So this would be n6 would be 9. We can then guess that n5 would have to be 11 and so on. You're always subtracting 2 to get the next term. So this tells us that n1 would be 19. Okay, so the arithmetic sequence, I don't think it's too mysterious unless you feel otherwise, and we can go ahead and expound on that. But otherwise, I'm just going to move on to review the geometric sequence. So a geometric sequence is one where one term in the sequence is simply a constant times the preceding term, right? So here we're given n1 and n2, and in general, the kth plus 1 term in the geometric sequence is simply a multiple. We'll call that r for common ratio times the preceding term, right? So while an arithmetic sequence is generated by addition of a constant, geometric sequence is generated by a multiplication by a constant. Okay. So you can take any two terms. So for example, I know that n2 should be the common ratio times n1. So any two consecutive terms, you can always get the common ratio by dividing one term by the preceding term. So n2 is 256 and n1 is 32. I believe these are both powers of 2. So 32 is 2 to the power 5, 64. This is 2 to the power 8. All right, there you go. Indeed, it's 2 to the power 8. So this is 2 cubed, or on your calculator, you don't have to do the exponents and the algebra and stuff, but it's just 8, right? So the common ratio is 8. So this means that apologize for that, n4 should just be the common ratio, which is 8, times the preceding term. Okay, so that would be 2048 times 8. I see that problem. Unfortunately, when I switch over, that works. Yeah, when I switch over to a different window, it makes the thing disappear. So let me see if I can fix that. I think I would have to minimize it. Yeah. So 8 times the 2048 is 16,384. It's not a connectivity issue. I don't think it's a connectivity issue on your end. When I switch over to a window, my OneNote disappears from the screen, but I think I fixed it. Now, we could find a general formula for this geometric sequence. N sub k, I guess, would be 32 times 8 to the power k minus 1. But I don't think you're expected to do that, so I'm kind of questioning my reasons for writing, even commenting on it. So let's just move on to another geometric sequence. Okay. So here we're given a sequence, but we're not given the first so many terms. We're just given two consecutive terms, right? So this means that n7 and n8 are known. But as soon as you have two consecutive terms, we know that one term divided by the preceding term in a geometric sequence gives you the common ratio. So that's going to be negative 18 divided by 54. So negative 1/3. Okay, so here it looks like we're generating the sequence by taking a term and multiplying by negative 1/3 to get the next term in the sequence. So I identified that common ratio. Let's write down negative 1/3. So how can we find n1 then? Well, if you get one term by multiplying the previous term by negative 1/3, you can go the other way by multiplying by negative 3. So here you'd multiply n6 to get by negative 1/3 to get 54. So n6 must be 54 times negative 3. So multiply by negative 3. And let's see. You could also use, I guess, the general formula. I didn't feel like doing the actual arithmetic, but I could use Excel to get that. I would probably use a general formula in my case. NK would be the first term, and then the common ratio to the power k minus 1. Just to so we know, you take 54 multiplied by -3 once, twice, 3 times, 4 times, 5 times, and 6 times. Okay, and this would give you that large number. Okay, but again, just to emphasize, as soon as you find two consecutive terms, find the common ratio. All right, and finally, for a geometric sequence, here you're given two terms in a sequence, but they're not consecutive, right? So you're given n5 and you're given n10, the fifth and sixth term. So we would say, well, n10 must be whatever the common ratio is times n9. But n9 itself will be common ratio times n8, and so on. N8 is the common ratio times n7. We can keep doing this until we get to n5, because that's the known term, the other known term. Okay, so what we have is that the 10th term, which is given, is r times itself 5 times over. So we can write that as r to the power 5 n5. So we can write down, apologies, we can write down the 10th term in the sequence, divide by the 5th term, and that should be r to the power 5. So this is, I believe on our calculators, this reduces to 32 over, what is 3 to the power 5? 243. And then to get r, I guess you would have to take the fifth root of both sides. And this turns out to be on the calculator 2/3. Yeah. So we found the common ratio. Right. So now if you have n5, you know that n5 is the common ratio times the previous term. And then n4 is the common ratio times n3, and so on. So now we have n5, we know. And then this is 2/3 to the power 4. So we can solve for n1 using basic algebra here. And I admit that this is definitely a calculator kind of number, so stick that into a calculator. So this turns out to be not a whole number, but it's okay. Anyway, so that was a quick review of an arithmetic and geometric sequence. Okay, and I did see problems on your practice or your review packet, whatever that was, of something called, well, okay. Does anybody have questions about geometric or arithmetic sequences? Okay, so let's move on to the hidden arithmetic sequence. Let's go ahead and take the first one, and just like for a basic arithmetic sequence, the difference between any two terms is a constant. In a hidden quote-unquote arithmetic sequence, you'll eventually get to the constant difference if you keep taking differences. So you can write out the given terms of the sequence, and then you're expected to find the last term, the next term, say. And so you take differences, right? So you go, well, -9 minus -8. It's the first difference. So one term minus the preceding term. So you get -8 plus -9 plus 8. So that's -1. And then you get -8 minus -9. So that's 1. And then you get 10, 26, Okay, and then you keep doing this. So now we have 1 minus a negative 1, which gives us 2. And then 9, 16, 30, 19, and then 49, so that's 20, 23. And then finally 9 minus 2, 16 minus 9, 23 minus 16. And so by the time you get this row of constants, differences, then we know that if we got these differences by saying, 9, 23 minus 16 is 7, right? Then we anticipate that if this row of constants continues, we put an extra 7 there, then you expect 23 plus 7 to give you the number here, so 30. And likewise, 49 minus 26 was equal to 23. So if that pattern continues, then we expect 49 plus 30 to give us the next term in the sequence. So that's 79. And finally, we get, this must be 77 plus 79 is 140 plus 16, 156. And so that's what we're after. It is a review, so I'm not trying to explain the procedure from the beginning, but if somebody wants me to slow down and do that more slowly, I definitely can. So now we can maybe try another one. What's the next term question, right? So they would state that it's a hidden arithmetic sequence, meaning that if you keep taking differences, eventually you're going to get the differences to be constant. Right, so the difference is 7, 11, no, 12, sorry, 14, 15. Okay, then you keep taking differences, so 12 minus 7, 15 minus 12, and so on. 15 minus 16, you get negative 1. Okay, so now finally 3 minus 5, 1 minus 3, and negative 1 minus 1. Okay, so we then assume that we can continue this trend of constant differences. And then to get the next term, you see that we would add these two numbers to get the next entry in the row above, and then we would add these numbers to get this, and finally 75 plus 12 gives us the next term in the sequence. So this is the no more question mark, that's 87. Any questions? Okay, let's go ahead and we'll come back to word problems. But let's look at set notation, right? So we were told that there were 3 ways that you can describe a set. Obviously, you can try English. You can use words to describe the set. You can simply list. Now, listing is one thing if, of course, you have a if the number of elements is a whole number. But if it's an infinite set, you might have to use ... notation, right? And then there's the set builder notation as well. And you should be able to kind of go back and forth between these 3 different ways of expressing the set. So you probably know this. So in America, the n represents natural numbers. In America, that means like the integers starting with 1, right? So these are the natural or counting numbers. So listing, of course, we just say it's 1, 2, 3, 4, and since this goes on forever, just use dot, dot, dot to indicate an infinite list or infinite set. You might be familiar with Z, which represents integers. And so these are of course, natural numbers, but with 0 as well. And then the negatives. So if I ask you, if I ask you for the complement of the natural numbers, using the listing method, I guess, or the roster method, well, you would have to say, well, what's the universal set? Well, we're talking about integers here, so I'm going to say that the complement of the natural numbers in the integers, so Z integers minus all the counting numbers. Okay, so set difference. Everything that's an integer but not a positive integer. Okay, so you would have, you're just taking away the positive integers here. So what you'd be left with is 0, -1, -2, and so on. And if you were asked to then maybe use words, right, to describe this new set, what phrase would you use, I guess? If anybody wants to suggest how we can describe this set using words. Well, I could do it as well. So, okay. We can't say these are negative integers, right? You can't say this is the set of negative integers. Does anybody know why this is wrong? Why this is not correct? Well, because yeah, 0 is not considered a neither negative nor positive, right? It's like this neutral, right, in terms of sign, integer. So instead, we can say it's simply the non-positive integers. It's the set of non-positive integers. It's like all the integers which are not positive, right? And so then the third way then to describe this set would be, I guess, using set builder notation. So here we're going to say that our set, the complement of the natural numbers, is all numbers where, first of all, it has to be an integer. And I'm using the conjunction symbol that you might have learned already. And that this integer has to be not positive, right? So at most 0. All right. So now what if did I have one ready? Yeah. So let's do another example. This time I'll start with a set builder notation. So we have a set A, and it consists of elements called K, such that K is 2 times n, where n is a natural number, and n is at most 5. So this is the set builder notation. Would we be able to then list all the elements here? It's a finite set, so. Well, we're saying n is a natural number, so but n is at most 5. So if you list those elements, right, it's a counting number, cannot exceed 5. And then here this says to double those. So it looks like this set consists of the numbers 2, 4, 6, 8, 10 as a list, right? And so, in words, what would we say that? How can we articulate this set just using a sentence or a phrase? You can use chat to type in an answer if you're interested. The natural numbers greater than 1 and less than or equal to 10 that are even. Perfect. Exactly. So this is the set of even integers starting at 2 and ending at 10 or at 10, I don't know. Great. So let's see. So that was just a quick review of the different ways of describing a set. All right. So now we're going to quickly review, well, we'll review the basic operations and relations on sets, right? Uh, I think I'm going to need, I won't need this too much at the moment. I'll definitely need this. So you all probably know if I say intersection of two sets, A intersect B, what's the symbol that we use? That would be the cap symbol, the upside down U, or yeah, or also the cap, right? As opposed to cup. So this is sometimes called the cap, and this is a cup. But exactly. And we write A intersection with B, and this is a collection. It's a new set that consists of all the things that are in both A and B. So we sometimes associate the word "and" right with that. Things that are both A and B. And so we see that that would be visually the overlap. So things that are in both A and B. And the quick aside, what do you call two sets whose intersection is empty in your class? So if there is no overlap of the two sets, we say that the intersection is empty. So we use the empty set notation. Okay. So these are called then either disjoint or mutually exclusive. I forget what term your professor used. Mutually exclusive disjoint. Okay. Mutually exclusive seems more like something you would use in probability or something. Like two things cannot happen at the same time. All right. So then let's recall the other binary set operation that's popular here. It's the union of two sets. And here we'd use the U symbol or the cup symbol. And we write the union of A and B. So these are things, this new set is all the things that are in either A or B, possibly both. So be careful, right? Colloquially, when you use the word or, sometimes we mean like it's A or B, but not both. It's one or the other. But in terms of sets, it's possible that you can be in both and still be in the union, right? You have to be in at least one of the two sets. So we would highlight that. It's like the melding of the two, the marriage of the two sets. And we also have the complement, which is probably what I should have started with. So the complement, we use let's say, complement of A, right? So it's usually understood what the universal set is. It's like the context, right, to the conversation. So technically, this is everything that's in the universal set minus what an A. So everything that's in the universal set but not in A. So that would be everything that's outside of A. Okay. Right. And so this is the set difference, I guess. Now we can then extend this to two sets where we might want to talk about everything that's in A but not in B. So everything that's in A but not in B. There's another way to write this, in fact. You can always write this as everything that's in A intersected with everything that's outside of B, right? So A intersect B complement. Those are equivalent. These are things that are in A and not inside of B. So that's exactly what that says, right? Everything that's in A but not in B. So those are the basic set operations. We also have a relation of subset, right? So if we say that A is a subset of B, we mean that in terms of Venn diagram, we mean that A is completely contained inside of B. Also, we can say that this means that any that's in A must also be in B, even though the converse isn't necessarily true. There could be things in B that are not in A. So this is the subset relation. And I guess I can mention it here. Um, the empty set can be written this way or that way, is always a subset of anything, right? It's also trivially, right, possible. We can say that B is a subset of itself. Any set can be considered a subset of itself. This is considered an improper subset because it's cheesy, right? So any set is a subset of itself, technically, but it's not a very interesting subset. So it's called improper subset. A set is just a collection of objects, right? Right. So both of these are sets, but a subset is just a sub-collection of a bigger set. Uh, so if set B is whatever contains the letters A, B, C, D, E, so that's a set of letters, I guess. And so if we want to create a subset, it's just a sub-collection, right? So we could choose to include A or not, right? Let's say we don't. We can choose B. We can include C, but we won't. Say we can include D and then E. So you see that every element that's in set A is also in set B. A is completely contained in set B. So A and B are both sets, but A is a subset of B. Everything inside of A is also in B. Now, the number, so might as well mention here, right, since we started talking about it, there is a formula for the number of subsets of a set. Let's just call that set B. So the number of subsets is 2 to the power, which is the number of elements in your set. And this includes the empty set and the set itself. Oh, okay. So this is considered an improper subset. So all you really want to remember is if they ask you instead the number of proper subsets. All that means is that we want to exclude B, right? Because that's just a silly subset. B is everything in B is also in B. That's kind of like silly to say even. So the number of proper subsets is exactly the number of subsets total, but then you subtract the subset, which is B itself. So that's simple enough. If you remember those two formulas for the number of subsets, take away the one improper one, right, the silly one, and then you get the number of proper subsets. So here, for example, the number of subsets of set B, well, there are 5 elements in set B. So the number of subsets is 2 to the power 5 or 32. It would be fun to list them all, but you have to remember that that includes the empty subset as well. But the number of proper subsets then, of course, is 31, if we don't include B as a subset of itself. All right. One more thing, notation-wise. So here's set B again. All right. My tablet is being a little laggy. I apologize. So it's true that the subset containing just the letter A, I mean, it's true that this set containing the letter A is a subset of B. But if you have a subset containing just one element, there's a more efficient way of writing that, right? So we just say A is an element of or in the set B. So that's just a reminder of what that little E means, element in or element of a set. Okay, so how would we write, let's say, the letter Z? Z is not an element of set B. So what's the notation for that? right? Z is element not, right? Not an element of the set B. Okay, so that's just a reminder of the notation. And then maybe we can move on to some more interesting things. So here, this is not Venn diagrams, but we're going to be given, or we're going to generate some sets and then look at intersections and all the operations, unions, set differences, complements, and all that. So I'm just going to work with letters because I'm pretty bad at coming up with creative sets. I don't know. Okay. So let's set A be the set consisting of all letters in the word algebra. All right, so how many elements will set A have? Very good. Very good. All right. I was, of course, waiting for somebody to say 7, but here, reminder that a set, right? All we can say about an element, right, is it either belongs in a set or not. There's never a question of how many times it appears in a set. An element can appear only once in a set. Right? You just want to know whether something is in the set or not. There's no question of how many times. So we shouldn't have repetition. So we see that there are 2 A's here. So 2 A's, but we can only write it down once. So we have A, L, G, E, B, R. Okay, set B is the set consisting of all the letters in the word geometry. So G, E, O, M, E, but we already have that listed. T, R, Y. Then we have the set consisting of all letters in the word calculus. We already have C. Now we have U. L is listed, U is listed, so now S. Perfect. And then the last one's just trigonometry, so I put it in there for. Okay, so let's look at, I guess, the intersection of A and B. So we know that this means that this set should be everything that's in both A and B. So it's good enough just to look at, let's say, the first set, set A. So A is in the set A, but it's not in the set B, so it cannot be in the intersection. And then we have L. That's in set A, but not in set B, so it cannot be in the intersection. G. There you go. It's in both sets, so it's in the intersection. So is E. B is in A, but not B. And then finally R. What about the intersection of B and C? Do sets B and C have any letters in common? So, not C, not A, not L, not U, not S. No. So this is the empty set, right? So you can write it either, with the brackets with nothing inside, denoting an empty bag, if you will, empty collection, or the empty set symbol. Now, again, quick aside, is this set empty? Is this empty? Empty set. Not really. I know that's kind of cheesy, but this is a set that contains an empty set. It's like having a bag inside a bag, an empty bag inside an empty bag, right? The outside bag isn't empty. There's something there. It's just that it's an empty bag. So this is no. So don't try to use both notations at the same time because then you get something kind of silly. The cardinality of the set would be 1 because it contains 1 element, while the cardinality of an empty set is 0. Now, do we have? Oh gosh, did I really make the universal set the whole alphabet? I did. Great. All right. Right, so I could have made the universal set a little smaller instead of the whole alphabet. X, Y, oh. I guess I just skipped ahead to the end. I got tired at the end. W, X, Y, Z. Good catch indeed. All right. So what's a complement? Again, it's understood what the universal set is, right? So that's everything that's in the universal set, but not an A. Also, if you'd like, it's U intersected with the complement of A. Well, all we have to do, I guess, is take the universal set and just take out all the elements that are in A, right? We want everything that's in this in the alphabet, but not in set A. Okay, so all we have to do is take out the letters in algebra. So A, L, G, E, B, R. All right. So if you so in terms of counting, if you know the number of elements in set A is, I believe, is 6, and I believe there's 26 letters. We are talking about a complement. The prime indicates complement. Oh, I see. Yeah, yeah, yeah. I apologize. There's so many different classes and these different notation that and the number of letters in the English alphabet, I believe, is 26. So how many letters, how many, what's the cardinality of the set, A complement then? Right. Well, it's just the universal set, number of elements of the universal set minus the number of elements in set A. So, uh, now, do we have any sets where one set is completely contained in another set? If you look at, looking at set A, B, C, D. I think so. I believe B is a subset of D. Okay, because all the letters in geometry are present in the letters of the word trigonometry. G, let's just check these off. E, O, T, R, and Y. So this is a proper subset, right? Because we see that there are, B is a proper subset of set D. Oh, thank you. Well, great. So it's still a proper subset because everything that's contained in B is also contained in D, but B does not equal D, right? They're not equal sets. They're not the same set. And how do you find so what would D minus B be? Well, it's everything that's in D but not in B. So it looks like the only letters that are in the word trigonometry but not in geometry are I and N. And this would be, there's two elements there. Yeah, we could take a union, so just to practice, I guess. So finally we can do a union of B and C. So to be in the union of two sets, we recall that means that you're in at least one of them, possibly both. So we can start by just listing all the letters in set B, and then appending any additional new letters from set C. So I see the letter C. It's not already listed. I see the letter A. That's not listed. And L is not listed. Neither is Z. Neither is S. Yep. Geometry calus. Right. Exactly. All right. Now, here, I'm going to mention what we call the addition rule, right? Before we start counting with, might as well, right? This is a good example. Well, now let me do that for the next one. Now, could we also create a Venn diagram using this? I think so. So let me copy the picture of a Venn diagram. Well, so to do this, of course, we probably want to start with a triple intersection. So the intersection of A, B, and C. Now, to be in the intersection of those three sets, you have to be in all three sets. But we already know that B and C are disjoint, right? there's nothing in common. So this is just the empty set because B and C are disjoint. So would there be anything in the triple intersection? No, right? I mean, intersection of A with the empty set. Well, you have to be in the empty set, but there's nothing there. So this is just empty. So the triple intersection is empty. And then we probably want to go on to the pairwise intersection. So A intersection B. So that would be over here, except we already said the triple intersection here is empty, right? So there's nothing there. So G, E, and R have to be in the intersection of A and B, but not in the triple intersection with C. Then let's look at the intersection of A and C. So you have A, L, so A and L. So again, the intersection of A and C is this, but we know that the triple intersection is empty. So A and L have to belong to the intersection of A and C, but are not in B. Okay. And then intersection of, well, the last pair, so B and C. And that's, we're being silly, we already know that's empty. So there's nothing here. Just 1 second. My tablet froze up, so it just takes a minute or a few seconds. Okay, so now that we've done the triple and the pairwise intersections, we can just go to the single sets, right? So set A, we already have A listed, L, G, E, and R, so there's only one letter left, B, so that must be exclusively in A, but not in B or C. In fact, you can probably write that set containing B is exactly the set of what's in A, but not in either B or C. Oops. So you might try to see how to write that. Of course, this is the A intersected with the complement of B union C. All right, so then we look at set B. We already have G, E, and R listed. So the letters that are exclusive to B, that are not in the other two sets, are M, T, and Y. And finally, set C, only A and L are in some intersection with another set. So C, U, and S. And then, of course, unfortunately, my choice of the universal set, I would write the rest of the alphabet outside. So here I'll go ahead and now mention the addition rule. So if you want to find the number of things in the union of two sets, this will be important for the counting using tables as well, is that you simply count the number of things in set A. Right. So when you do that, you like get the crescent part of A. So you count this region, and then that intersection part of A, right? So those two distinct regions give you all of A. And then to that, you would add the number of things in set B. But when we account for set B, we're counting the crescent part of B and the intersection part of B, which then you see a problem in that you've overcounted the intersection by once. So what you do is you subtract the number of things in the intersection of A and B once, not because you're not counting the intersection at all, but because you're counting it twice, so you got to compensate. And that way you count each region exactly once. So this is called the addition rule. So they might ask you for, didn't want to erase that. So if you want to count the number of things in A or B, again, we said that it's according to the addition rule, to count the number of things in A, number of things in B minus the intersection. The number of things in the intersection. Just to be clear, the intersection we already know is consists of 3 letters. So the number of things in A, number of things in B, minus the number of things in the intersection. So that's 10 items. That's using the addition rule. Of course, we could have just counted, right? So if we go to the Venn diagram we created, if you want to count things that are in either A or B, you say 1, 2, 3, 4, 5, 6, 7, 8, 9. B. How many things in B? 7, 6. Oh, I'm missing O, aren't I? Right. Yeah. In set B, we have the letter O. I forgot to write that one. So indeed, I apologize for that. We have 10 letters in the union of A and B, and we've computed that using the addition rule as well. So 10 letters in the union. Now, if you wanted to know the number of things in B or C, right, you'd use the same formula, the addition rule, if you want to be formulaic. But if B and C are disjoint, they have nothing in common, their intersection is empty, what's the number of things in the intersection? Well, a number of things in the empty set. Well, obviously 0. It's an empty set. So this addition rule simplifies in a sense because, for disjoint sets, the intersection is empty. So that we can just leave that out. So that's just 6 plus 7, 13. Right. And again, we could, if I didn't make another mistake, we expect 13 letters here. So let me try to clean this up a bit. All right. So we're counting the number of things in the union of B and C. And indeed, that's 3, 5, 8 plus, oh no, 5, 8. Is that 13 letters? Oh, I just used the wrong numbers. What's the number of elements in set B? That's 7. I just copied the what I had above, and that was silly. And the number of things in C is 5. Indeed, that's 12. So that's correct. Any questions about Venn diagrams, at least for, let's see. We can probably practice some more after we go through the problems that were prepared. I think what we're going to do is we're going to play a game where you write down some sets with operations of intersection, complement, union, difference. And then we should be able to shade the correct region. We'll play that game. And maybe also for practice, you can try shading a region, right? And then trying to find the correct expression that describes that region. So, all right, but here this is counting, right? So now I don't care what the sets contain or not. All I care about is how many elements we have in these sets. So I listed all the sets in the top row. So you have the universal set, the triple intersection, the pairwise intersections, and the single sets. And below are all the cardinalities, the number of elements in each of those. Okay. And so if you want to start counting, if you want to fill in this Venn diagram with the number of elements, right? So it's no longer the elements in the set, but how many we have that I'm going to be writing down. You would probably start with the triple intersection, right? So the triple intersection says that there are 5, right, elements. In the triple intersection, the number of elements is 5. So we go to the Venn diagram and write 5 there, indicating that there's 5 elements there. Okay. Once you stop with the triple intersection, you go to the pairwise intersection. So you have that the number of things in the intersection of A and B is 6. But you have to remember that the triple intersection is already contained in the pairwise intersections, right? So A intersection with B with C is contained in the intersection of A and B. So we already have, when we're talking about the intersection of A and B, we're talking about this whole part. But we already have 5 elements in the triple intersection. So there has to be one element in the intersection of A and B, but that's outside of C. If that makes sense. If you add 1 and 5, you get 6. And you can then maybe practice writing down like the what this region is that has cardinality 1. Okay, this doesn't mix colors. I thought it would be like watercolors or something, right? Yeah, it doesn't. All right. So I'm talking about this region here. You can say the number of things in that region. Well, first of all, that's the part of the intersection of A and B. But then you have to exclude things that are in C. So you'd say it's the intersection of stuff that's outside of C. And that would have cardinality 1. We could also write this as the intersection of A and B, but stuff that's in the intersection of A and B, but not in C. So the set difference, that's equivalent. So now we look at, let's say, the intersection of B and C. That's in here. And in that intersection, this is telling us that we have 5 elements. Okay, so how many elements are there going to be in the intersection of B and C, but not in A? But that's stuff that's not in A. So we're talking about the intersection of B and C, but outside of A. So we're talking about this, I don't know what that shape is. It's like Star Trek or something. How many elements in that region? 0, exactly, right? Because all 5 already accounted for in the triple intersection. This should be 0. There's nothing here. So now we have the number of things in the intersection of A and C is 8. So there should be 3. Very good. So there should be a total of 8 elements here, but 5 of them already in the triple intersection, so there must be 3 of them that are in the intersection of A and C, but not in B. Very good. So we're well on our way to completing this Venn diagram with cardinalities. We finished all the pairwise intersections of sets. So we'll move on to the single set. So set A has 15 elements. A6, very good. 7, sorry, we already have 9 of them here, right? So 9 plus 6 gives us the 15 total that should be inside of A. And how would you express this set here? So in words, this is everything that's in A, but that's outside of either B or C. What's the symbol here? Well, you can just literally write that down. Right? Stuff that's in A, but not in the union of U and C. So this is one way to write it. That would be 6. You can also, of course, write this as A and then intersection of everything that's outside. Oops, I messed that up. Sorry, that should be everything that's in A, but not in the union of B or C. And that's equivalent to A intersection with a complement of the union of B and C. Those are equivalent. All right, now the number of things in set B is 16. 6 of them are already accounted for here. So we must have 10 exclusively in B, right? So the number of things in set B, but not in the union of A or C, is 10. And finally C, there's 12 elements in set C. 8 of them are already accounted for, so that's going to be 4, I guess. Thank you. Okay, but now that we have this completed, one more thing. There are 50 elements in the universal set, so there's a total of 50 over here, right? Make it look like a 5. So how many things are outside of A or B or C? So the number of things that are in the complement of the union of if you marry all three sets and just look at the outside of those sets, what would that be? Maybe it'd be wise to look at the number of things in the union. I think it's 21. I think you're right. So how many things are in the melding of all three sets, the triple union? There are 29, and we don't have to do very much, right? We're not going to use a overcomplicated addition rule. We're just going to count how much we have. So that looks like it's 17, 20, 25, 29. So then if you want to know the number of elements in the complement of that triple union, then you would say it's just the number of elements in the universal set minus the number of elements in the triple union. So that's 50 elements in the universal set, 29 in the triple union. So that's 21 outside. Very good. YE. 21 is everything not in the Venn diagrams. That's right. That's outside the circles. All right. So maybe you can imagine they can ask you all sorts of funky questions like how many elements do we have in the union of A and B, but not in, let's say, C. Equivalently, so everything that's in the union of A and B, but outside of C. 17, I think so. C, so we count things that are in the union of A and B, but outside of C. So 6, 1, and 10, right? You're in either A or B, but you cannot be in C. Indeed, 17. Very good. All right, so that's kind of counting with Venn diagrams. Just to remind you, probably want to, if you're given uh, the information, you'd want to start with a triple intersection, and then do the pairwise intersections and the singletons, or the single sets. All right. Any questions about this exercise? So then we can also count with tables, and I was kind of imagining a survey, not very creative. So I'm thinking about North America, and then three countries: Canada, USA, and Mexico. And then let's say we surveyed some people from these three countries, and we asked them their favorite flavor of letter X, Y, or Z. And these are the survey results. So can somebody tell me in a table like this counts? Let's say, what does this 3 represent? Just so we know how to read this. That represents a number of people in the survey, if you will. How many in Canada chose X? That's right. So this is the number of people surveyed that were from Canada and preferred the flavor of letter X. So in such a table, the numbers are how many things are in the intersection of the categories in that row and that column, right? So the number of things, number of people who were American and liked flavor Z is exactly, you find USA, in the row, and you find Z in the column, and the intersection at the intersection in the cell of the intersection gives you the number of people there. Okay. All right. Now, what about if we start asking things like how many Canadians were in this? How many Canadians were present in the survey? What would you do? That's right. So the number of Canadians is just the row total for Canada. Exactly. So you just add these up, right? 3, 1, and 4 is 8. Now, you can articulate what this has to be true because you want to take the number of Canadians regardless of what flavor of letter they preferred, right? So it doesn't matter what letter they like. So Just add those up to get 8. So likewise, the number of Americans would be 4 plus 2 plus 5. And the number of Mexicans would be 26, yeah? And then how many total people, if you will, so the number of people in this survey are being our universal set, yeah? Well, you can just add up all the numbers in the grid, or you can do the same thing as just do the column total here, right? So this is 19 plus 26 is indeed 45. And so likewise, how many people in the survey preferred flavor X? Yeah, that's right. It's a column total now, right? So the number of people who like X regardless of their nationality. So you just add across the nationalities. Right, beautiful. So it sounds like you're familiar with, and of course, if you add these numbers up, you should get 45 as well. As a quick check. 7, yeah, indeed. All right. So then they're going to start probably asking you questions about like how many people liked flavor X or flavor Y. Well, so to be counted among these people, you can like either flavor X or Y, right? So we just count the number of people who like flavor X and Y. And so you can use the addition rule. And these tables are set up where these are disjoint, they're distinct categories, right? We don't have people who like both X and Y. So the intersection is just empty here. That's 0. So 8 plus 13. Yeah, we're just adding these people. Okay, well, what about the number of people that are either Canadian? Sorry, I'm fighting my tablet if there's pauses where I'm not writing. Okay. The number of people who are Canadian or American, and um, they like flavor X. That's correct. So when we take the union, all we're doing is lumping the Canadians and Americans together, right? And at the same time, we're looking at category X. So the intersection is 3 plus 4. Right, intersection 3 plus 4. Okay, what about the number of things which number of people who are Mexican and they don't like flavor X? So the to not like flavor X means that you must like one of the other flavors, right? It's like you have to choose one of the flavors. So that would be not X means that it's either Z or Y intersected with the nationality here. The intersection is 10 plus 15 people, so 25 people. Right. It's everything but X in Mexico's row. That's correct. Oh, how complicated can this get? I don't know. Oh yeah, union. So what if you have the number of elements, the number of people surveyed that are either American or they like Y or X. So people are saying 6. So so would you add all of America and X and Y? Yeah. Well, be careful, right? It's a union, right? So here we can just count. Like you take USA and then you union that with X or Y. So I should use blue. So you have like a marriage, right? So you have to count everybody in there. And I just lost a number. What was that number? So that must be 10. So I mean, a table like this is like a Venn diagram. But it's not circles, right? Uh, so when you take the union of all these three sets, we should count all the Y's and all the US, right? So that's 3 plus 1 plus 4 plus 2 plus 5 plus 1 plus 10. The 26, I believe somebody said. Right. And exactly. I mean, we can definitely use the anytime you have a union and you're not sure, just remember that when counting, well, when counting the US, right, we counted these two cells. And when counting X or Y, we counted all these cells, but so we've counted, you double counted these. So that sounds like addition rule, right? So you could have said, well, this is the number of Americans plus the number of things that are either Y or X minus the number of things which are both. Addition rule. Okay, the number of Americans is 11. The number of things which are either Y or X is 21. And the number of things in the intersection of Americans and X or Y is 6. So that is 32 minus 6. So that gives me 26 using addition rule. So what's the number of things that are either American or Mexican, or people who like Z? No. We could 41. So we could use addition rule, remembering that you always have to subtract out the intersection once. So the number of people who are either American or Mexican are 27. The number of people who like Z is 4. And the number of things in the intersection is 20. And I guess that has to be the last example for this problem since I completely destroyed. So 21, is that right? So we get 4, 2, 5, 1, 10, 15. Wait a minute, did I do some bad math here? How many people are either American or Mexican here in this table? Oh, 37, not 27. Gotcha. I'm just not sure. Oh, I accidentally erased a number, so this should be 24. I think that's why. There you go. Sorry about that. So we have 50, 11, so 61 minus 20 is 41 indeed. So 41 is correct. Very good job. All right. Now let's see, what else do we want to cover? I skipped word problems. And again, I took some questions from the art of problem solving from the past. That's 2010. So I don't know how many, what were the things that I saw in word problems. Well, I'll just start them. All right, so if Biftu gives a penny, gives me a penny, I will have twice as many pennies as he has. If I give Biftu a penny, he and I will have the same number of pennies. Oh my gosh, how do you translate? How can we translate this into what are the two unknowns? Well, so I guess this is one approach, right? It's just that you name your unknowns, like there's me and or Biftu and I, or whatever. Yeah. So those are the unknowns. Correct. So we have Biftu has some number of pennies, and I, yeah. So Biftu has X pennies. I have Y, say. Okay. So now we're just going to try to translate this into algebra. So what does it mean? What expression gives you what happens? Like Biftu. Biftu gives you a penny. How much money does Biftu have at that point? What expression? Well, X minus 1, yeah. Then how many pennies do I have? Y plus 1. And then this says that in that case where, Biftu lost a penny, then I must have gained a penny. I have twice as many pennies. So should we write Y plus 1 is equal to 2 times X minus 1? Or is the correct expression X minus 1 is equal to 2 times Y plus 1? Which one is the correct expression? I have twice as many pennies. Well, so if I have twice as many pennies, if you do a thought experiment, so I might have 10, right? So Biff2 in that case will have only 5. So whose number do you need to multiply to get equality? Right? You need Biff2s, right? You need to, 2 times 5 would give you 10. I have twice as many pennies, so like I have 10, they have 5. So you have to multiply Biff2's amount to get my amount. So it's actually the first one here. So we have the equation that y plus 1 is equal to 2x minus 1. Uh, I don't know, how much algebra do you actually do? Because I'm a little afraid I might make this too much. That's one equation. So then we have another scenario, right? So if I give Biff to a penny, he and I will have the same amount. Okay. So highlighting that, let's write down what that means. So I gave Biff 2 pennies, so I have y pennies, and I gave one away, and then Biff 2 gained that penny. Okay, now they're saying this is easier, right? Because now they're saying the amount of pennies we have is the same. So that's another equation, or if I should say y is equal to x plus 2, yeah? And then we can solve this system of 2 equations to unknowns. Probably in the first equation, right, we can replace y. We see that y is really x plus 2, so we can substitute. Oh, you haven't? Really? It was on your review. They had some, like, there's a shelter, you have cats and dogs and things like that. So this was so I don't know. All right, so yeah, I don't know. Maybe you can ask your professor, because I was just going off the types of problems that were on your review sheet, your review problems. So x would be 5. Um, and if x is 5, y is 7. So it looks like Biff2 has 5 cents, so I have 7 cents. Oh, okay. Tables? Well, all right. Well, so maybe I won't go over all these word problems. It's 3 o'clock, but I'm happy. Where did the y plus 3 come from? So for the first problem? Oh, okay. So in the first piece, the first sentence, the information. So in that first sentence, Biff2, after giving me a penny, has this much. I gain the penny, so I have this much. And then I have twice as many pennies, so you need to double Biff2's number of pennies to equal my number of pennies, because I have the larger amount. Then you distribute, and I could have brought I think I just added 2 to both sides. I don't know why I did that. So you left with 2x on the left side, but you have 1 plus 2 or 3 on the right side. I'm not sure why I wrote it that way. I should have maybe written this as y is equal to 2x minus 3. Okay. Okay, good. So are there questions that anything you're concerned about, an example of a particular type of problem you'd like to see before we quit? Yeah, I see. So this is that question from the review about Jamil having only 5 cent and 7 cent stamps, and we need a total postage of $1.30. What is the smaller number of stamps required? Maybe this one's kind of related, because there's a maximum and minimum kind of concept involved, right? So obviously, if you want to minimize the number of stamps, you want to use as many of the large denomination stamps as possible. So use as many of the 7 cent stamps. So this is kind of silly, easier than that one. but I thought it would be familiar. So find the maximum minimum number of coins when using the denominations of, quarter, a dime, a nickel, needed to make $1.15. It's that kind of problem. Now, if you want to find the maximum number of coins, yeah. So if you want to find the maximum number of coins, which denomination would you want to use, right? Well, the smallest one. You want to use the 5-cent pieces, so you can use as many coins as possible. So that would be just the maximum number of coins would be the 115 cents divided by 5 cent in a nickel. All right, so that's 23. So that's the maximum number of coins. All right, and so how would we determine the minimum number of coins? What principle would we want to use there? Yeah, you want to use as many of the large denominations as possible. Yeah, it's kind of intuitive because it's money. So we kind of have a feel for that. But so to get the minimum, you want to use as many quarter pieces as possible. So how many quarter pieces would we use? Well, 4 of them, right? So you have 4 times 25 cents. So 4 times 25, that gives me 100 cents. So how much is left over if you have 100 cents? Where do you put the cent symbol? Is it in front or after the number? Does anybody know? Anyway, you have 100 cents already, so you need 15 more cents. You want to use the next largest denomination, so you can only use one of them, one 10-cent piece. So that's now 110 cents. So you have 5 cents left over, so you got to use a nickel. And so here I'm not trying to be like all difficult here. I'm just reviewing that principle that if you want, the minimum number of things, use the larger denomination, the largest denomination first. Okay, so here we used 4 quarters, 1 dime, and a nickel. So that's 6 coins is the minimum. I think of a similar flavor, but not as easy because maybe it's not about money. And this will also betray the fact that I don't cook. I have no idea if these proportions are even plausible here, reasonable. So we'll do one more. So in this problem, we have a recipe that calls for 3 eggs, 8 ounces of flour, no idea how much that is, and a 1/4 cup of water. I guess we're making some sort of dough. In order to make, and this recipe makes 4 servings. Okay, so how many servings can we make if we have 2 dozen eggs, 60 ounces of flour, and 2 cups of water? How would we go about? It's a very similar principle, right? Because the number of servings we can make, the maximum number of servings, is limited by our materials, right? So how many eggs do we have? Yeah. So 22 dozen, yeah. So we have 24 eggs, right? And then we have 60 ounces of flour, and then we have 2 cups of water. All right. So if you're just looking at the eggs, right? How many recipes can we make, if you will? How many servings can we make? Well, each recipe, one recipe, and by the way, you already know this, but you're free to go because it's over time, and my tablet's freezing. Yay! So we have 3 eggs per recipe. If I can get this to work. Sorry about that, but I'm just going to finish this at least for the recording. So, all right. So one recipe calls for 3 eggs, right? Now we have 24 eggs, and then we know that one recipe also makes 4 servings. So doing the kind of dimensional analysis, whatever this is called, the recipe stuff cancels out, eggs can cancel out, and we're left with 24 servings, right? If you're just thinking about the eggs, right? But then we're also limited by the amount of flour. So one recipe calls for 8 ounces of flour, okay? And we have 60 ounces of flour. And then we know that each recipe also makes 4 servings. So noticing that what units cancel out and doing the multiplication across, we get 4 times 60 divided by 8. So that's 30 servings, right? All right, so here, what are we limit? And let's do the same thing for water. One recipe calls for a quarter cup of water. Now we have 2 cups, and then we know that each recipe makes 4 servings. Multiplying across, we get 32 servings. So 8 divided by 1/4 is the same as 8 times 4. So that gives us 32 servings. So what are we limited by most, if you will? Well, the eggs, right? With 24 eggs, yeah, with 24 eggs, we can only make 24 servings. So we cannot make more servings than the eggs allow. The eggs is the bottleneck, right? So 24 servings. So I saw something like that, but I guess maybe that's I don't know. Hopefully that's a close enough approximation to what the professor is thinking. All right. Well, thank you for being here. I really appreciate it. And good luck on the exam. Thank you.